everyone, this is Mike Human for G2M Research, and welcome to our webinar on the explosion in imagery from radiometry, cryo-EM, and other imaging technologies. Can storage keep pace? I'll just kind of introduce the topics a little bit and go through the agenda. So at the beginning here, I'll spend a couple of minutes on going through the ground rules. A couple quick things to make life easy. Please, if you have any questions, use the Zoom Q&A feature to submit those questions. We'll hold all the questions to the end. When we do the audience Q&A, we'll answer those questions, but feel free to submit them anytime during the discussion. We're also recording this, and a copy of that recording will be made available to everybody who's registered for the webinar. We'll send out a link probably on Thursday with that, as well as a PDF of the slide set. And they'll go out to everybody again who's registered. So with that, let me kind of jump into the topic and introduce a little bit. So there's really been a huge explosion of data from imaging technologies. And it's not just that more images are being taken, it's that the technologies being used are also growing as well. You think it's things like cryo-electron microscopy, computerized axial tomography. Of course, that's kind of one of the older ones that's been out there for a long time. MRI, PET scans, SPECT scans. There's just new technologies popping up all over the place that can produce huge amounts of very, very high resolution images that then can be oftentimes analyzed by artificial intelligence or machine learning techniques to take this data and try to identify disease early and or increase the efficacy of treatments. And if you look at the amount of data being generated by it, this is just PACS and hospitals alone. As you can see, the amount of data between 2005 and 2015 increased tenfold from that time to now. And I couldn't find later data in that, but I'm sure it's probably increased at least tenfold in the past 6 years, if not more than that. Building responsive storage architectures becomes very critical for this. If you think about training artificial intelligence and machine learning algorithms to help identify diseases, obviously the faster your storage is, since that's probably one of the biggest contributors to performance, the quicker you can train things and the quicker you can get algorithms that work. And from a storage requirement standpoint, there's a couple of things that are important. Obviously, bandwidth, latency consistency are all important. The availability or the ability to do multi-tiering so that you can use on-premise storage for your very fast storage, use cloud data storage outside to do all your archiving, things like that, and then data management. What data is where, who has access to it, what's it been used for, which models has it been used to create, and as we iterate on our models, how do we use that data effectively? Those are some of the topics we'll be talking about today. With us are Matt Hallberg. Matt's the Senior Product Marketing Manager for Kioxia. We also have Shimon Ben David. Shimon is the Chief Technology Officer at WECA. Esteban Rubens is the Principal in Healthcare AI Practice from NetApp. And I'm Mike Human from G2M Research. Let me turn it over to Matt now and go ahead and take it away, Matt. I think you might be muted, Matt. Let me grab the mouse quickly, Matt, and see if I can unmute you here.
Sorry, I had to switch from full screen to smaller.
Okay. There you go.
All right. Hi, everybody. As Mike mentioned, I'm Matt Hallberg from Kioxia. For those not familiar, we're an SSD vendor, one of the bigger ones in the market, formerly known as Toshiba. And today I prepared some materials to talk about some of the cool things that we've been doing in this space. So we have done some work with MIT and some other labs, and we've done a presentation. We've done some presentations at various trade shows and whatnot, of doing real 3D exploration of whole brain images, where we would capture images using expansion microscopy, which is essentially embeds an object in a water absorbing polymer and then physically expands it, and then takes really high res pictures, and using high speed flash storage, SSDs, and low latency networks will allow us to, in real time, be able to, have scientists, basically scroll through a brain, move through a brain. Kind of like if you have ever watched a really cool high, one of those science shows, like, fantasy science shows like Star Trek, being able to move images around of a brain. So we were able to do that using our SSDs. And let me get a little bit more into that demonstration. But first, let me also point out that, as mentioned previously, the sizes of these files, as you take these high res pictures, is getting larger and larger and larger. And we're at, terabytes of data for multiple images. And when you're trying to render real time, you need to be able to have, don't know why it's playing, you need to be able to have hardware, not just SSDs, but hardware around it, and great software around it, to be able to manage the random and sequential reads and writes that are going to and from the storage medium, like SSDs, through CPU, DRAM, graphics card, and whatever else. And where we believe is one of the more important links in the chain there is through storage and everything that's around the storage. So 8K images were used. 8K images are important, as you see in the notes here. It accommodates the various spatial scales within the brain, where neurons are linking the small processes that are nanoscale size. And 8K is able to get really detailed visualization in scales of a 4-digit order. I'm not a scientist, so I cannot answer what exactly that means, but I've seen the demo. It was super impressive and insane when you think about, looking at an image of a brain and being able to move through it in real time. Okay. There's rendering and other images that are going on here. So I look at storage from two different perspectives. I look at storage that's locally, meaning, if you're doing anything with AI or ML and you're doing your training sequences or whatever else, that's all data that's local to the GPUs or whatever you're using inside the system that's basically processing the data. The training phase of machine learning is obviously, well, at least in my opinion, the most resource intensive set of operations. The data sets that I mentioned, to be able to show a whole brain image, that's a lot of pictures, and that can reach up to terabytes. And those training sets can be thousands of images. So we're getting, close to like an exabyte for a single run through of a brain. And whether you're running on RAM, DRAM, or on local storage, the local storage needs to be able to handle reads and writes as quickly as possible. So that's where we tend to move towards technologies like NVMe and NVMe over Fabric, where you can take advantage of PCI Express Gen 4, or we announced Gen 5 speeds, to be able to queue up, read, and move data to GPUs that are on the bus. Gen 4 SSDs, there are very noticeable benefits. We're seeing 7,000 megabytes on reads and 4,200 megabytes on writes. And when you're on random, we're talking about SSDs that are capable of million plus IOPS and high random writes as well. And also, when you get to the later NAND nodes that Kioxia, along with other NAND manufacturers, provide, the NAND itself is getting denser, and you're able to drive capacity in a small 2.5-inch form factor drive. So for instance, CM6, our enterprise class NVMe SSD, we have up to 30 terabytes in a single 2.5-inch 15-millimeter SSD. And so there's also remote storage. That's basically where your data lake is. And you want to pair to your data lake, a high-speed network interconnect. There's been a lot of great improvements in that aspect over time. There's 200 gig NICs. GTC is going on. I'm sure they're announcing something cool at GTC, maybe 400 gig NICs, who knows? But we've seen a lot of advancements and a lot of adoption for like Rocky V2, NVMe over Fabrics. There's been a lot of adoption in the market. We've seen VMware and Azure announce support for NVMe over Fabric. Anyways, so the storage that you have available in the data lake, you want to make sure it's not as robust as what you may have inside of your compute node, but it's able to deliver the data that's being either onloaded or offloaded from your compute node. And so we rely on guys like NetApp and WEC.io to be able to basically help chug the data in, chug the data out. And we feel NVMe is the best place for that. If you have an NVMe over Fabric set, to have high bandwidth, low latency transfers between your data lake and the data that's sitting on the compute node. Because the faster you can get data in and off of the compute node is the sooner your GPUs can go start chugging data again. Okay. So this is just a quick demo we did where we saw, pretty big performance boost by going from PCIe Gen 3 to Gen 4. I won't spend a lot of time on that. And then, we also have another cool product in the works called Ethernet Bunch of Flash. Essentially, you're able to put a bunch of drives into what we call an Ethernet bunch of flash. You may notice like a JBOF, but this is Ethernet attached, where you have Ethernet on the back of these boxes, and all the drives are high availability. You can see them on the network. We've done some cool demos with some HPC players using Lustre. So there's just more to come for the environments where you need to take data in and out of the network really quickly. Since I'm running low on time, this is just a quick overview of the drives that we support today. CM6, Gen 4 SSD, we're FIPS certified for those medical, the applications that require that the data on the drive is encrypted. And for those of you who may or may not work with government entities that require FIPS certification, we support that with our drives, as well as the other product here, CD6. Similarly, FIPS 140-2 certified, single port, capacity up to 15 terabytes. And with that, I'll go ahead and apologize for running a little bit over and turn it over to Shimon.
Thanks a lot, Matt. Shimon, let me give you control. Hold on 1 second. All right, you should have the mouse now.
Great, thanks for that. So, see, hey guys, my name is Shimon Ben David. I'm the Chief Technology Officer from WECA. And okay, I think right and left have been next year. So what I really wanted to do today is start with the correct slide. Obviously, that would work. On. Okay, so get back to the initial slide. I think the slide transition is a bit slow here. So
yeah, sometimes the first click takes a second or two.
Okay. Okay. So yeah, we fixed it. So what I really wanted to do is to take a few minutes and talk about the challenges that we see in the life science environment, present WECA as a storage environment, as a data platform, and then go over a real customer use case and kind of like connect all of the dots and show how WECA really helped that customer. So jumping through it. So what we really see at customers is a plethora of environments. So I think, Matt, you mentioned local environments. So you mentioned GPUs with local drives. And by the way, this could be on cloud or on-prem. So GPU servers with local drives. Usually the beginning of the pipeline, whether it's genomics, whether it's Cryo-EM, it's usually derived by a number of sequencers or scopes or cameras or any other IoT environments, generating the data and pushing it to some sort of shared environment. And by the way, the requirement for a shared environment here is usually because it's aggregating massive amounts of data from multiple devices, and also because of the protocol, SMB. Usually that's built into these environments, these scopes and IoT devices, and then either copy the data to local GPU storage, local NVMEs to be analyzed and trained on, or just run the pipeline on top of that, GPU accelerated or not. And then sometimes in many cases, copy it to some sort of HPC storage environment for faster analysis, faster shared analysis. Additionally, copying the data to a DR data copy center, so you can have backup in DR, because these samples are very expensive. So you don't want to lose that data. And then in addition, using some form of HSM to create a backup in an archive to the cloud, to an on-prem, to a tape device. So what we see is that there is a lot of data movement in these environments, and managing data movement is expensive and it's not simple. And if we look at the reasons for the data movement, the different storage environments, they're because of different protocols. So some protocols SMB, some would require GPU or GPU direct storage, some would require POSIX semantics or S3 semantics. So there's different protocols involved. There's also different performance characteristics. So a NAS appliance would usually not be fast enough for real intensive GPU workload. An HPC system storage would, but it's very limited on the IOPS, so it's not suitable. Copying the data to local NVMEs is interesting, even though it limits the scalability and so forth. So data copy is being done due to protocol, due to performance, and also due to price. So looking at Weka, what we wanted to provide and what we are providing customers is, what if you could have a single environment that created a shared environment, shared file environment that supported all protocols, S3, SMB, NFS, POSIX semantics, and GPU direct storage. It supported all aspects of performance, throughput, IOPS, latency, and metadata performance. So in essence, it would be even faster than your local GPU servers and NVMEs, because eventually what Weka does, and I'll present it, is we aggregate multiple NVMEs and present them as a file system, not as a block device. That's ridiculously important. And then the cost perspective of it, we also are able to mitigate cost by having an NVMe tier and a larger object storage tier. And additionally, what if you could have that same platform move the data around for you where you don't need to manage that? So that's a win-win-win. That's exactly what we show customers as a value. So kind of like our key design points are simplicity, speed, and scale. So if you could have the simplicity of managing a file system and the shareability, so you're not managing block devices, you're not managing separate NVMe fabric LUNs where you just need to manage them per server, but you're managing a file system. And everybody can share the same data. The file system takes care of the multiple access and the locking. Having said that, it's not a regular NAS environment. Weka is not a regular NAS appliance. It's a high performance environment. So the speed that we provide there is in the tens or hundreds or terabytes per second. It's also in the millions of IOPS. So you can have the cake and leave it all, right? You can have the throughput, the IOPS, the latency, and the metadata. So in essence, you don't need even local NVMEs in your GPU server. So you reduce the cost, you reduce complexity, and it scales out. So you can scale to petabytes and exabytes. And we do actually have customers in the petabyte ranges where the system manages those millions or billions of inodes, as well as the data movement. So a typical Weka environment would look something like that. And this is an abstracted layer. You would have your compute servers running your multiple relevant applications and pipelines. It would support all of the protocols that I just mentioned, containerized or not containerized. And it does support diverse workloads. And that's the key factor, because you usually don't use a parallel file system, because a lot of your application workloads are small IOs. And with Weka, because we designed the system to provide small IOs as well as throughput and metadata, you replace the need to copy the data to your local NVMEs. And as I mentioned, you have the Weka Flash tier that moves the data and expands the capacity between on-prem and cloud as well. And as an example, imagine a worker in a data center expanding the data center, the capacity of the flash tier to an object storage tier, but also sending the data to a remote cloud, could be AWS, could be something else, could be another data center, and then allows the bursting of that data to that secondary site. Maybe for a DevOps environment, maybe for a QA or dev environment, maybe also for a backup in a DR. So the unique thing is that the system also manages that data movement. And when you talk about millions and billions of files, that's mandatory because no other third-party data mover application can do that. I talked enough, I think, about the storage characteristics. Now, where does it really translate? And I wanted to present a real use case by a customer that are doing AI accelerated life science workload. So with this customer, Atomwise, they needed massive amounts of small files, and that's very typical in many of these AI use cases. Initially, we were thinking that AI use case, definitely the image-based use case, would be only a large amount of large files, but we see more and more that there are multiple image-based AI environments that actually utilize massive amounts of small files. So in this case, they needed 200 million small files. Their GPU servers that were processing that were really starving because they were using either local NVMEs, which weren't fast enough to feed the GPUs, or some sort of shared storage, or a combination. And in this case, they actually had a requirement to run it in the cloud. So they were testing on what would be the most efficient solution. And this is a very interesting use case. What they do is they're trying to find binding between different protein and other chemicals, and they actually are using AI to predict the correct binding, saving a lot of time and effort and actually money in doing that. So they actually, as they presented that, again, this is part of their presentation, they actually use the convolutional neural network to actually map the image of the molecule, and therefore make it easier to find the binding affinity. They had numerous amounts of protein targets and compounds to work with, and eventually that translated to more than 15 million experiments. And with Weka, actually, what they found is useful is the IO performance was, in their words, phenomenal. Their training time dropped by up to 2 times, so 200% of what they used before. And again, this is on the cloud. This could be also on-prem. It could be even better. The ability, the first bullet, it was quick to set up the server and sync RS3 data to it. So the ability to use the Weka system to have the fast flash tier and have the Weka system throw the data between different environments, between different S3 environments, was very unique and very compelling. And eventually, it's been an ideal match for distributed deep learning with large files inputs. So the ability to use the large file inputs, small file inputs, and combine that as part of their AI pipeline was very unique, and Weka was able to help there. And I think with that, I'll actually stop, because we talked about the Weka capabilities, we talked about the values and what it can actually provide in real use cases. With that, I'll actually hand it over to Esteban.
Thanks a lot, Shimon. Those are some great images you had there, by the way. I like that.
Yeah.
All right, Esteban, let me get you set up for remote control here, and I'll let you go ahead. You should have control now. I think you might be muted.
Somebody has to do it every presentation. So it's a 2021 kind of mandate. So
that's right.
All righty. So, okay. So talking about these kinds of large images that are getting created, my background is in healthcare IT. I come from enterprise imaging. So beyond the traditional areas of radiology and cardiology, we now see even outside of research, we have all these other specialties generating huge amounts of data. And a lot of it, as some of you were pointing out, it's visible light. So it's not just X-rays or basic inferring images from radio pulses like an MRI. This is cell assays, right? It's videos of sleep labs or gait analysis for orthopedic surgery. So really huge amounts of data, some for clinical use. As you can see here, data consumption is either for screening purposes, diagnostic purposes, whatever you want to define AI as, so training some kind of neural network or clinical trials. And then, of course, you got to be able to give access in any format, any protocol that is necessary. So when let's look at digital pathology, for instance. It's an interesting example because it's an emerging area that we're doing a lot in. It has very low penetration worldwide, whereas if you look at PACS or DNA, radiology, cardiology, that's probably in North America, Western Europe, kind of Asia, sort of anywhere that's more or less has a well-developed healthcare system, you will find essentially enterprise imaging across the board, at the very least radiology and cardiology. Digital pathology, probably even in North America and Western Europe, maybe 10% of institutions have it. It is a huge opportunity because everybody's starting to adopt it, to digitize that workflow, going from having glass slides that you have to keep forever to being able to collaborate and just all the obvious things that you get with digitizing that workflow. So the end result, and you see here, either 0.5 micrometers per pixel or 0.25 micrometers per pixel, you end up with multiple tens of gigapixel images. So each image from the scanner, after compression, we're talking about a gigabyte. And so, of course, each case consists of multiple images, so you get very large very quickly. This is one of our customers. You can see the stats there. They end up with a requirement of 1.2 to 1.7 petabytes a year. And this is just one hospital. And then another one, 880 beds, not huge, not small either. It's kind of a large mid-sized hospital in the US, 500 terabytes a year for digital pathology. So really, really large amounts of data that are required. And of course, you need to provide the right performance at the right time, but not forever. And sort of that's the key thing that I'll cover in a minute here. Then when you go to AI, you have all these different areas. Of course, the overall idea here is you're trying to prevent the phenomenon of GPU starvation, like Shimon was talking about. That's very important because if you have starved GPUs, they're idle and they're essentially wasting money. It's expensive to either stand up an on-prem GPU compute environment or consume GPU or TPU or any other kind of specialized AI hardware in the cloud. And not to mention some of the more advanced ones like Habana Labs that was acquired by Intel, or SambaNova that we do some work with. They need even more performance when they're doing their analysis because they can process that much more data than even GPUs, right? Even when you look at the latest NVIDIA A100 and the DGX A100, well, when you look at what some of these other companies can do, that is mind-blowingly more. And so the requirements for all of us in the storage and data management world go way up. So of course, it goes without saying, I don't want to repeat what Matt was talking about. So, NVMe and NVMe over Rocky and everything that we can do to provide that, we can all do that. That's kind of table stakes, going 100 gigabit Ethernet, 200, now 400. And that absolutely is required. But what do you do afterwards? So for us, the important thing, moving again beyond those table stakes of you have to deliver the performance when it's needed, is the idea of the data fabric, of having the right data in the right place, the right time, at the right price, crucially, with the right access characteristics. So whether you need NFS or SMB or iSCSI or S3 or anything else really doesn't matter. And beyond that, so that this idea of having the right data in the right place, the right time, seamlessly, right? So you want to move data seamlessly from and to any cloud. So the realization of this multi-cloud world, we have ONTAP as our operating system for our, everything we do on-prem in the cloud. So it really doesn't matter. But the point is moving data very, very easily. And even now, more and more, we're starting to see model training from object storage, whereas until maybe even a year ago, pretty much it was all NFS. Now we're starting to see more emphasis on high performance S3, which is maybe counterintuitive, but still it's out there, something that people are talking about. So we end up with this idea that really we don't care where the data lives. We don't care if you're on-prem, if you're file or object, you're software defined or hyperscaler, or you have a private cloud. We want to make sure that we provide this seamless experience no matter where the data is. So the idea is we keep the data at the core. That's the heart of everything we do. And so the customer decides where they want to keep the data and what they want to do with it. And we just give them the tooling to be able to have the data, again, in the right place at the right time at the right price, without having to refactor applications or really do anything else that is disruptive. And then on top of that, again, it's probably not unique. Certainly, we just heard it from Shimon, cloud tiering. We want to make sure that we can take those least access blocks, sub-file elements, and move them off to any cheaper storage, whether it's a local S3 bucket or a hyperscaler S3 bucket, or really anything else in between. And the realization of that is what we do. And so, this is what it looks like. It's what you would expect, whether it's on-prem or in the cloud. We really don't care. Again, it's all about agnosticism and making sure that that experience is seamless. So if you look at what we're doing with Amazon, we do something very similar with Azure and soon to be with Google. We have a first-party service. So when you go create a storage volume in AWS, if you want files, it used to be that you got FSX for Windows or FSX for Lustre. Now you have FSX for NetApp ONTAP. And so that is an AWS product, a service that you consume from AWS. You don't really have any dealing with NetApp directly. And within those FSX for ONTAP volumes, we have this tiering, right? So we use SSD, AWS SSD storage, and also S3 buckets. So when you're thinking about, for instance, enterprise imaging, like a PACS or a VNA, the ability to do that seamlessly within the FSX ONTAP volume is very important, because the application doesn't have to be aware of it. Because otherwise, many applications in healthcare, like clinical applications, have not been built with this kind of tiering in mind. So it's important to be able to deliver that. And I think I'm probably running over, so I'll very quickly give another example. It's one of our customers. I was mentioned before, the cell assay imaging. They do hundreds of millions of images per year. And this is a very interesting use case of both. It's a hybrid cloud, right? They acquire those images all over the world. They have many labs globally. They all go up to AWS for normalization and feature extraction. And then that data is actually moved to an on-prem data center in Europe, where they have DGX A100s, and they do that training locally, because for them, that makes more sense, but they do both, right? So the feature extraction is on using AWS EMR, and they're training models both with images and metadata, with the features that they're extracting. And so just in closing, this is what I've been describing, right? This is ONTAP at the heart of everything. And this idea of the data fabric and agnosticism, we really don't care where the data is. It's all the same to us. NFS, SMB, block, S3 really doesn't matter. It's about choice and seamless kind of application of this. So thank you. And with that, we'll move on.
Thank you very much, Esteban. Let me jump to the panel questions here. First question, and we'll have Shimon go first, then Matt, and followed by Esteban. And that question is, the number of imaging technologies continues to explode, providing a great number of new sources of medical bioimaging. Do these different technologies present the same or different issues for storage?
So I think the different imaging technologies present different challenges, because every technology is generating different types of data sets, and then these different types of data sets then need to be addressed specifically. And I think, as we mentioned part of the conversation, some of these data sets could be massive amounts of images, film-like, video-like, or small images-like, and then the storage needs to be able to address these accordingly. Also, every different image also uses different protocols to push and pull the data in and out of the storage system. So that should be accommodated for also.
Excellent. Matt, what do you guys see from Kioxia's standpoint? I think you're on mute.
All right. From our point of view, it's, I mean, for SSDs, we got to be able to design controllers and, you know, what drives the media usage inside of the SSDs to handle the various sizes of files and everything else. But from the most part, I mean, we're used to small packets, large packets, etc.
Got it. And Esteban, on the NetApp side, do you guys see large differences in the types of data or the problem based on the medical imaging technology used?
Yeah, there's certainly some of that. So for instance, I'm thinking about one of our customers that's doing, it's more research. It's a research hospital, and they're doing molecular imaging. So this is sub-cell imaging, and they're going to end up generating, it's a special kind of microscopy, not Cryo-EM, it's a different kind. They're going to generate about 350 terabytes per run of that experiment. So it really changes things, because all of a sudden you really worry about the edge. So this is going to be an edge to core to cloud use case, because you need the massive ingest performance, and the camera vendor, these special cameras that are attached to the microscopes, they have special requirements. So there are PCIe boards that you have to put in PCs basically, and they have requirements about, you know, the kinds of NVMe drives that have to go in there for acquisition. They even call out a specific kind of hardware RAID board for RAID 0, and then we have to aggregate that, and it just changes really everything at the infrastructure layer too. Not just the storage infrastructure, but just for the physical plant, because they can't put things in this lab because it's a very controlled environment. So they're going to have to run fiber. So we can do at least 100 gig Ethernet to what we probably would call the core, but that's not going to be the core, because it's probably going to be somebody's office, because it's too long a run to their data center, the hospital's data center, that is where it's not possible to go with 100 gig Ethernet. So it really, this is a deal that we have in flight right now. And it's very interesting, because it's not the case that the application is just running in the core, and then you have a bunch of either imaging modalities or cameras or whatever sending data in, and you end up with huge amounts of data. Here, the speed of acquisition is really fundamental. So it again underscores that you can't just focus on core or cloud, you just have to worry about the edge as well.
Excellent point. Okay, with that, let's go to the first audience survey. And that question is, I'm going to launch it right now, is How large are the imagery training data sets that you and your customers typically field? This is a pick one. We'll give you a couple of minutes to answer that. And while we do that, let's go ahead and go to the second panel question. And that question is, are there specific areas where NVMe and or NVMe over Fabric provide unique benefits to large imagery storage solutions? We'll start with Matt, then go to Esteban, and then to Shimon after that.
And I didn't mute myself this time, so.
Oh, there you go.
Actually, I touched on this during my presentation, and I'm sure the gentleman on the call can agree with me as well. But really, again, NVMe and NVMe over Fabric, the promise of high bandwidth performance and low latency, I mean, that just spells awesomeness for large image storage solutions, right? If you're dealing with large files, single file that's super large, the faster you can move it around is the faster you can load more files, or again, the faster you can offload files. And if you're running NVMe over Fabric infrastructure, again, it's not only are you doing low latency, high performance, or high bandwidth reads and writes inside of your systems, the outside of the systems where the network is are also bursting with low latency and high performance.
Excellent. Esteban, I'm sure you guys are familiar with both these technologies at NetApp. What do you see as their value?
Yeah, so this is, again, one of these, it's become table stakes. You absolutely need NVMe storage. So I'll make a distinction there. NVMe media is absolutely table stakes. NVMe over Fabric is not that widespread in healthcare, at least. I don't see that. There's some discussion, but it's not widely adopted. So much more widely adopted is 100 gig Ethernet for typically AI training applications. So that would be within an environment where you have GPU compute, you have NVMe storage, and then you have 100 gig, and that is within the rack. This microscopy case that I was talking about is the first time I've seen it outside of the data center, really. So kind of for AI training, it's absolutely mandatory. For older applications like PACS, at least the cache has to be on NVMe. Certainly not everything. There's really very little benefit. I think, yes, of course, I agree. Eventually, hard drives may end up disappearing, but at this point, 7.2K drives are still really part of the equation. So NVMe is crucial. You can't really do anything in healthcare or life sciences without NVMe storage now. And then, we'll see the jury's out as for what NVMe over Fabric is going to become.
And with that, let's go to Shimon. I'm sure you guys have a strong opinion on NVMe over Fabric, Shimon.
We have an opinion on everything, but I'll try to narrow it down to this question. So yeah, NVMe is definitely an important component. I actually agree with Esteban that NVMe over Fabric is less. To me, NVMe over Fabric is more of a compromise. It's more of an attempt to repeat what we did in the SAN area, or the same time frame where you had multiple block devices aggregating to a centralized storage. So NVMe is the natural evolution of that, but it's not a revolution. It's only a basic evolution because you're still doing the compromise. You're still saying, hey, I have a lot of fast devices, NVMEs. Let's aggregate them and try to manage them as we did before. And again, I also agree that now that you see Ethernet environments going to 100, 200, we already have customers running 400 gigabit Ethernet. So suddenly doing that game of compromises using NVMe over Fabric to manage different segregated block devices doesn't make sense anymore. Also talking about I think we should also look holistically at the entire pipeline of these imagery workloads, and they're never composed out of a single application. Esteban mentioned a core to edge to cloud, and we definitely see all of that. And you see that during different phases within that environment, within that pipeline, you do have different storage needs. So for example, the NVMEs are very important for the high performance Cryo-EM pipeline or a genomic sequencing pipeline, or if there's a combination of AI on top of that. But then you do want the deeper storage, the more cost-effective storage to be there also for your HSM, for your backup in DR tier, which you wouldn't necessarily. So definitely NVMe is important, but you should also revolutionize the NVMe with Fabric. You shouldn't just go to that.
Perfect. Okay, with that, let's go to audience survey question number 2. I'll launch that. And that question is, when looking at storage solutions for medical bioimagery, what are the critical factors that drive your technology and architecture choices? And this is a check all that apply. Again, we'll give a couple of minutes to for the audience to fill those out. Let's go to panel question number 3. And that question, and we'll start with Esteban first, then go to Shimon, and then to Matt. And the question is, obviously, AI and ML are being utilized to analyze all the images from these various sources. How can storage architectures be optimized to speed up the training learning process for imagery? I know we talked a little bit about this, so if you have any parting thoughts on that, Esteban.
Yeah, I think it's all about flexibility and data movement, because you're going to end up with petabytes, or even at this point close to exabytes in many cases of data, but you don't need that all for training. The training data sets are just a subset of the whole data set that has been acquired. In research, they want everything, and they want to keep it because they need to work on explainable AI, and they need to be able to help with reproducibility. So having a storage environment, an architecture that allows you to very simply curate those training data sets and move them to NVMe, right, for the purpose of training, and then kind of that back and forth, whether on-prem or in the cloud, that's huge. So for me, it's really about that seamless data movement that matters.
Excellent. Shimon, what do you guys think?
So from our perspective, definitely storage has many capabilities. So if we're talking about speed, and again, usually we would like to look at the process as a holistic process. We never just the training or the learning. So first of all, how do you get the images from the equipment? Is that in an efficient way? Do you need to constantly worry about copying the data manually, or does the storage does it for you? How do you train and perform the training and the learning process on them? To give an example, with Weka, we support the new NVIDIA protocol of GPU direct storage. So imagine a GPU server that is now doing 40 times the work of a regular shared environment, or 10 times the work or 20 times the work of a local NVMe. So that really speeds up. Eventually, it decreases the wall clock time. So also then the ability to move the data. For example, if you need to burst, maybe you don't have enough GPU servers on-prem, and you need to move the data to the cloud, and then run any GPU direct storage or just any GPU analysis on the cloud for that data. So there's the ability also. And I would also mention, because that's one of our key values, as I showed in the presentation, we see a lot of image data, which is composed out of different data types, different data sizes, data sets. So the ability to say, hey, we can accommodate, or the storage can accommodate in a shared file environment for all different types of images, size, and IO types that are needed is mandatory. And that really accelerates the overall workload.
And Matt, what do you think on this question?
From a SSD point of view, I think we're pretty in line with where things are. We're doing what we can. We're trying to saturate buses and things like that. I think there's some cool technologies that were introduced in NVMe a couple revs ago that, maybe hopefully will come to the forefront eventually. Things like controller memory buffer, where you're able to leverage some of the DRAM that's on board the SSD itself as an addressable area, where you can do things like NIC offloading, where you can do caching and things like that directly to the DRAM at a much faster speed than you would, going through to the medium that is NAND. Things like that, more advanced features, but definitely not like mainstream adoption features. But really just specialized. This is what the drive needs to do. This is how the NIC, how the OS, how everything's going to take advantage of it. Those are the kinds of applications and things that need to happen in the future in order to keep moving progress, especially as these training sets are exponentially growing.
Thank you very much. Okay, one question we had to do actually with the training set size. And that was, obviously we talk about training data sets can be petabytes or even larger. What is typically seen by kind of, if you have a look at the average of your users, what is the typical size that someone should kind of plan for in that respect? And I'll throw that out. If Esteban, you want to start off and then go to Shimon and then to Matt, we can take turns trying to answer the question.
Yeah, so for academic medicine, it's usually in the hundreds of terabytes. So probably like between 500 and maybe 2 petabytes or something like that. For life sciences, it's much larger. It's probably between, kind of low single to like 10, 15 petabytes. And then genomics, pretty much, it's not imaging, but kind of up there too.
Wow, that's pretty big. Shimon, what have you guys seen?
Yeah, I think we see a similar thing. So with medical imaging, we see terabytes. You see devices that are working 24/7, generating images at the 2 to 5 terabyte per scan. And then it's funny because then it's all about how do you create a fast offload of the data out of the the scanner, so then you can generate more data. With genomics, I think as Esteban mentioned, we see gigabytes. The thing is that there's a lot of need to save all of that data constantly. So you never want to throw it away because sometimes you literally have only one chance to generate the data. So then, even though sometimes you're creating only gigabytes of data per scan or single digit terabytes, then eventually the data sets become huge and you're saving petabytes of data.
Yeah, that's a good point. And Matt, what about you guys? What have you seen?
Well, I'm going to have to defer to the experts and Esteban and Shimon. I mean, we as an SSD company don't really get exposed at the system level to these kinds of applications unless we're working with a partner or doing the research ourselves. But yeah, I mean, what we've heard conjecturally from our own work and from our customers is terabytes.
Excellent. Well, with that was the only question we had. To remind the audience, we are recording this. We'll make a copy of the recording available to everybody. Probably in a day or two, I'll send you an email if you've registered to let you know where that's at, as well as a PDF of the slide set. Again, thank you to our sponsors, Esteban from NetApp, Matt from Kioxia, and Shimon from WECA. We really appreciate your guys' support, and thank you very much.
Thank you.
Thank you, everybody, for attending.
Thanks,
Thank you very
everybody.
much, guys.
Have a good day. Bye.
Thanks.